Hello online students. I decided to make another video because I did have a few questions about Module 2, so I'll explain some of that along with a slideshow. Okay, so I go into explaining what an action potential is. And the reason why I do this is because both the book and the content talks about depolarization and repolarization right away, but they don't really explain what it is and why it's happening. So when you get deep into muscular anatomy and movement science, we talk about how the body, to create every bit of movement, whether it's voluntary or involuntary, we need a graded potential to happen and a synapse to go through the muscles from the cells to get the movement happening. And that is typical when you're dealing with energy or any type of cellular process. So we need an action potential. And essentially what an action potential is it is a change in the positivity and negativity of the surroundings. So when you're moving things through a cell wall, they have a threshold of where exactly the graded potential needs to be, and they've measured it in millivolts. So to create an action potential, to create an action happening, we have to get to -70 millivolts. Now, one of the ways that I describe this, that everyone kind of has seen happen before, if you're watching a football game, say our Baltimore Ravens, or even if you're watching a soccer game, something international that anyone would see, they always do the wave in the stadium. Now, sometimes you see this starting, and then it makes it about halfway and it fizzles out. The same thing happens with action potentials. And it's also similar to a roller coaster. If there is not enough momentum in going down the roller coaster, you won't go up the other end when it's time for the car to go back up. So essentially what we're trying to do is generate enough energy to create this action potential and to create the whatever action that we want. And here it just is showing how there are positive ions going through to the extracellular fluid to create the difference that's negative across the inside of the membrane, just to create this energy that is in this particular picture. But I wanted to describe that a little bit, and this is an overview of the events that happen during a change in a neuron. So, and a neuron is a nerve cell, and they look very much like this. We're not going to get too much into the anatomy of the cell, but essentially the nerve cell is creating some action potential. So a depolarization is a reduction in membrane potential, and hyperpolarization is going beyond what the potential needs. So for instance, if we needed to go to -70 and it goes a little bit further to -80, that's called hyperpolarization. So then we go into repolarization, which gets things back at 0%. So these are changes that cause a current increase or decrease in the action potential. So this is just showing an example of how this works on the membrane of the cell on the cellular level. So here is the foot of a nerve cell, and this is, the dendrites that come out of the nerve cell, or at the end of an axon, the foot. So this gets into contact with the next nerve cell to create the chain of electricity that goes from cell to cell. So a depolarization happens here at the clef, and it usually happens from a neurotransmitter going through. So, and neurotransmitters are different chemicals that go through your body to cause different reactions. So this is how the electricity is passed from cell to cell. And these electrical passes of energy are called synapses. So synapses can go from neuron, from neuron to muscle, or from neuron to gland. And what causes, so the first from nerve to nerve causes sensation. The second one from nerve to muscle causes the muscle to move. And then the third one, neuron to different types of glands, will cause a gland to release some type of chemical that we need. So I do go into detail about that because I want you to know the why of what's happening in our heart when our heart beats. So and here are some neurotransmitters involved in action potentials or synapses. You've heard of most of them. Norepinephrine, I'm sure you've heard of, epinephrine, serotonin, glutamate, and GABA. Acetylcholine, maybe, maybe not. But here are some of this is what the chemical structure looks like. Here's the mechanism of action, and here's the location of how it happens in different, bits of information to back up the why of what is going on. So we're explaining all of that to discuss the action potentials of the heart. So as the heart squeezes, the ECG measures the action potential and measures the activity that's going on. So when the atria squeeze, we get the P wave. And then when the atria stops squeezing, we get the segment. And then when the ventricles squeeze, we get the QRS movement. And then there's a point that stops, and then there's the T. So each of these movements are called a depolarization. To get the heart beating, it needs a depolarization. And then it goes back to repolarize, and that way it can start another movement. So here we discussed the structures that are involved in the electrical waves. So we have the SA node, sinoatrial node, the AV node, the atrioventricular node, the Purkinje fibers, and then the ventricle. So the squeezing goes in a wave-like motion as the signal is passed from the SA node to the AV node, to the Purkinje fibers, and then to the ventricle, and across the heart. And here is the dotted line of the movement that you can trace. So this particular information is on every ECG, EKG test. Even though we really don't use paper anymore, this is how we determine the movement. So you will see in class, or, I guess in some of the examples, we use them on paper as the examples that I show you. But at this point, a lot of them are electronic, but they still use these squares. And they want you to know that the speed of the paper goes at 25 millimeters per second, or that's how slow we are counting for the movement to go through of the heart. Each tiny box, the small boxes, are 0.04 seconds. A large box is 0.2 seconds. And so 5 large boxes is 1 second. And you will see, when you see 5 large boxes in a row, there will be a gradation line. And so this is 1 second, 2 seconds, and so on. So here we go. And here, they've blown this up. So here they do the gradation of time a little bit wider and goes across. And I'll show you on another sheet that we'll be looking at. So even though we don't really print on paper so much anymore, when a printout of an ECG comes out, it is printed out on grid-like paper, or you'll see it on the computer grid-like. All right, so here's a review of the leads. So we discuss and talk about the leads in a closed vacuum, just because we take the leads like a triangle, and this is how we add and subtract them. So it's called Einthoven's assumption. He got the Nobel Prize. So what we are treating the body like is it is a closed vacuum, and that way we can talk about negative and positive charges throughout the vacuum. And so we will talk about that more later. You will see several different leads. Here is lead 1. It goes from the right arm to the left arm. Lead 2 goes from the right arm down to the hips where we put the electrodes, and then lead 3 goes from the hips up to the left arm. So if the potentials of two of these are known, we can figure out the last one. And that makes sense from what you've learned about with geometry. So essentially what we do here, and this is how we figure this out, when we add lead 3 plus lead 1, we get lead 2, and I'll show you how that works. I'll show you how that works in a minute. But here we are. Now, this is called a 12 lead system or a 12 lead hookup, and here's why. The 6 leads that you use on the chest are called precordial leads, pre meaning before and cordial meaning heart. So that's 1 through 6. Those are the 6 easy ones that you can get right away. The augmented leads, we'll talk about it in a second. And then these bipolar leads are the ones that have all of the positive and negative, and those are the leads 1, 2, and 3, as I showed you earlier. So very often students will say, there are 6 leads on the chest, and then 2 on the shoulder, and then 2 on the hips. So why isn't that a 10 lead system? It's 12 leads because of the data points we're counting. So there's 6 on the chest, there's 6 bipolar leads that make up the triangle sides 1, 2, and 3, and there are 3 more leads that are unipolar. They're augmented limb leads. And so this is the augmented limb leads, and I'll show you in detail what they mean in just a moment. So this is what I was trying to show you earlier. Say in segment 1, this accounts for 3 total squares. And in segment 2, this goes negative about 1.5 squares. So if we know positive 3 plus negative 1.5 will equal positive 1.5. So 1 plus 3 equals 2, and so on. So you will see that if you know 2 sides, you can figure out the third. Here are your 6 precordial leads. And then you guys have already seen a sample of that. And so what I want to show you here is that here's the repolarization and depolarization of the heart. So it squeezes and then it needs a repolarization. So the atria squeeze right here and then repolarize here. The ventricles squeeze right here and then repolarize here. So the T wave is repolarization. The P wave is the atrial depolarization, and the QRS is the ventricle depolarization. So how to get a good ECG tracing? You clean the area with alcohol prep and allow it to dry. You may have to use cleaning prep to abrade the skin. You may have to shave the area if you are in the hospital. You make sure you get a low impedance, and what impedance means is the connectivity between the electrode and the chest. You make sure the electrodes aren't loose, and you get little as possible movement artifact. You may have some muscle twitches and you would have to do it again. So here's an example of artifact. This is because the electrodes aren't put together, aren't tight enough to the chest. So this is bad impedance. And this is just a movement artifact. See, the ECG is fine here, there's some movement, and then it goes back to being fine. So we determine the rate, the regularity, we analyze the P waves, we determine the intervals, we identify and analyze the QRS, we determine the site of origin, identify the dysrhythmia or arrhythmia, and evaluate its significance. So I am going to start a second video discussing this in detail.